Okay, in this video, I want to show how to use SageMath to study the abelian groups Z mod NZ, sometimes written as Z subscript N, and then also another completely different group, the units in the string Z mod NZ. That's denoted Z mod N, Z subscript N with a times symbol. And the group operation in the second group is multiplication. The group operation in this first group is addition. All right, so let's do a simple example. So let's take G. Oh, I should say beforehand that there's two ways to go about doing this that I know of so far. One is using the command integers followed by n, where n is a specific number like 10. And then, or you could use another function called AdditiveAbelianGroup. And then here you need to put the n in square brackets. Well, when we talk about more general additive abelian groups, we can put multiple numbers in the square brackets. And so that's why we need the square brackets here. Okay, so let's start off with this additive abelian group. And let's start off with n being 10. And let's list the entries of this group G that I've created. And yeah, now unfortunately there's these extra parentheses around each of the entries, but that will make sense not in this video, but in a later video when we talk about how flexible this additive abelian group function is. But okay, so basically it's the numbers from 0 to 9. That's what the numbers integers mod 10 are. Those are these remainder classes. And okay, so then we want to pick out one of these, like 4, say. And then you need to do what's called coerce the 4 coerce Sage into thinking that 4 is an element of this group. Okay, and so the way you do that is you take the number 4. Again, because we're working in this additive abelian group thing, you need to put it into square brackets. And then the notation for coerce, in other words, tell Sage to think of this number 4, not just as some random integer, but as an element of this group G, is G and then round brackets, and then you put the 4 in there. And again, 4 in square brackets. Okay, and so this element B, or we're going to assign it to this, this element B. Okay, so B is then this element 4 in our group G. And then I want to ask, what is the subgroup generated by 4? Now, to do that, we need to use this command submodule. There's a reason it's called submodule, not subgroup, which we'll understand maybe later. But anyway, so we start off with the group G, and then we create the submodule generated by B. Once again, we need to have square brackets when we're working in this additive abelian group situation. Okay, and then that, let's ask what is the elements of H, so H.list, and then you see the multiples, the multiples of 4, if you will. Now, here I was puzzled, why is 2 appearing first? Well, it doesn't list them in the order that you would necessarily compute them in. So you'd first start with 4, then you'd go to 4 plus 4 is 8, then 8 plus 4 is 12, but then you're in mod 2 land, and so the 12 turns into 2, then 2 plus 4 is 6, and so on. Okay, so, and 6 plus 4 is 10, which is 0. Okay, so that's the H. Now, incidentally, if you didn't know that command, one way to see what's available, so once you start your, have your subgroup, and then you can press H dot, and then hit the tab command. And then you can see all these methods or attributes or functions that are available to the object H. And then one of them was list all of its elements. Where was this H? Okay, so, and then that's a method, so it needs to have some parentheses. Okay, then we can also ask for the order, and that's, okay, 5. That's because how many times do I have to add 4 to itself to get back to the identity element, which is 0? So I have to add 4 5 times, namely 4 plus 4 plus 4 plus 4, basically 5 times to get back to 0. You can also just do regular addition in this group. Let's actually make things more interesting by adding a third instance of B. And so B plus B plus B is indeed 2, because 4 is what basically B is. as an element of this group of mod 10, integers mod 10. And so 4 plus 4 plus 4 is 12, and then mod 10 lamb, that's 2. And then we can also ask for the order of a group or subgroup. And so now that happens to be 5, which is the same as the order of the group it generates. Yeah, okay. So that's using this function, the additive abelian group function. I haven't quite talked about z mod nz times, again, the group of units. And for that, I'm going to need this other operation, other function, integers n. Okay. Now, this integers n, that's actually a ring. In other words, it has both the addition and the multiplication that's coming from the integers mod 10. So first of all, the command is, set r equals the integers and 10. Now here we don't have any square brackets. It's just one round bracket. Whereas by contrast, if you're calling the additive abelian group, you need to put square brackets. If you don't put these square brackets, you'll get some error. So that was very confusing for me to understand the syntax. And I'm calling it R because it's a ring. We'll learn about rings later, but it's basically where you have both addition and multiplication. The addition gives a group structure. The multiplication might not give a group structure. Anyway, so let's just list all the elements. And then here, yeah, the list is 0, 1, 2, 3, up to 9. And there's no annoying parentheses like there were up here. Okay. So that's what we're expecting. And then if I want to list the elements of the multiplicative group of units, there's a specific command, which again, I found by doing r dot and then hitting tab, and it gave me the list of suggestions. And these are 1, 3, 7, and 9. These are the elements that have a GCD of 1 with 10. So for example, 2 is not in here because 2 and 10 don't have a GCD of 1. And so no power of 2 will end up giving 1. And so you can't form a group out of multiplication. Anyway, so these numbers here form a group under multiplication, whereas these numbers up here, 0 to 9, they form a group under addition. Now, unfortunately, I can't quite seem to just ask for, what is the order of 3? Well, I can actually. That's what I did next. See, so I want to pick one of these elements like 3. And again, I want to tell Sage or coerce Sage into thinking of this number 3 as an element of this ring R. And so this is the notation. Now, again, there's no square brackets around the 3. Previously, in this, using the additive abelian group, you need to have these square brackets. So that gave me a lot of confusion. So by contrast, when I was trying to coerce this element 4 into this group G, I had to put square brackets around it. Here, when I'm dealing with the integers function, that I don't need to. And again, it kind of makes sense to me now. Okay, anyway, so now we've got this element C that's basically referring to this 3. Again, R of 3 is coercing Sage into thinking this 3 is an element of this ring of integers R. Okay. All right, so then I can ask C.order. I can ask for the order of C. And it's going to give me the additive order. It gives me 10. And that's because how many times do I have to add 3 to get to the identity element in this group? This is a group with addition. And again, going back up here, there's 2 completely different groups, even though the notation is very similar. This here is a group with addition as the operation. This is the group with multiplication. In the case that n is 10, this group has 10 elements, whereas this group with multiplication has only 4 elements. So they're very different, even though the notation is very similar. And we're going to ask, what is the order of 3? And the order of 3 is 10. That's under the group under addition. Then if you want the multiplicative order, then there's the command multiplicative underscore order, which again, I found by typing C, typing the dot, and then hitting tab, and then there's a whole slew of options. And multiplicative order is 4. Why is multiplicative order 4? Because it's asking how many times you have to multiply 3 by itself to get 1 mod 10, to get a number that's 1 more than a multiple of 10. Well, 3 to the 4th is 81, which ends in a 1, and that's the smallest power of 3, positive power of 3 that ends in a 1. Okay, so then in terms of generating the group generated by 3, I only could think of a silly or naive way to do this, and that's just using a for loop to compute the powers, for example. So let L be the multiplicative order. So here that was computed to 4, and so I'm just saying now I'm computing this for loop. So for I in the range L, which again, this range L is the numbers 0, 1, 2, 3 in this case. Since L is 4, it stops 1 less than the stopping point. Okay, and so these are the powers of C, the multiplicative powers. And so this is the group generated by 3 in this multiplicative group here, 1, 3, 7, 9. And so this group we see is cyclic because it's generated by 3. Then if I want to know the additive group generated by 3, it's a similar for loop, but I do, instead of C raising it to the ith power, I do I times C. And so I start with 3, 6, 9, 12, 15, and 18, and so forth. And I started out with I equals 0. So, okay, there.